Our first speaker is Meg Schwamb. There we go. We see your slides, Meg, so that's good. Great. Okay. So first up, we have Meg Schwamb talking about an overview of Sorcha.
You want to mute them, just in case.
All right. Can everybody hear me? Hopefully.
Yes, we can, Meg.
Perfect. Always bad to try to give a virtual talk and then not find out that you've been muted. So I'm giving a really quick update on Sorcha, which is a solar system simulator for LSST that's built around rebound assist as our ephemeris generator. I should say is I'm really not the person that should be giving this talk. It really should be this entire group. This has really been a big collaborative effort to try to get this beast of a software package basically through the finish line because of just the sheer challenges of LSST data scale and rates. So really it's these people that deserve all the applause and credit across the board, especially Steph Merritt, Gregory Federer, Sam Cornwell, as well as Pedro Bernardinelli and Jake Kurlander have done a huge amount of work, as well as Matt Holman and Mario Urich has been definitely key in helping us as well. So those are the key sort of, again, scientists thinking who've been really helping, as well as the Link Frameworks team, and many of them are listed here. So I don't need to tell you why LSST is awesome. I don't need to tell you why it's cool for solar system science. What I do need to tell you is I think a little bit of what my motivation was for trying to get Sorcha out the door. And that was the idea that if you really want to actually compare the intrinsic true model of any solar system population, you're going to want to try to at least figure out what the model you'd expect to see in LSST data, right? And do lots of the awesome things that if you're out of solar system, people you're well aware has been sort of the bread and butter within the ASOS and CFEP surveys that have done a really great job of exploring and characterizing the Kuiper belt and its structure and the transit-tuning region. And so do that by like building a survey simulator, and then you forward bias your model to what you'd expect to see. And so that's probably the best way, right, to figure out, right, what the intrinsic population looks like from your LSST observations. Except it's really kind of hard because this is a 10-year survey, multiple filters, huge data rates, that this is not like that every other survey simulator we've tried is not fast enough or not as easy to build on top of to use for LSST rates. So we built from scratch in Python a thing that we think is doable in terms of being modular, that if you don't like what we have and you want to put it in your own phase curve functions, you can, right? But that also takes into account all the things that are and the peculiarities within the Rubin ecosystem that are important, right, for figuring out what you could detect in terms of solar system objects. So that includes footprint, the camera footprint, right? It's not a perfect circle. There's detector raft, there's gaps in the rafts and detectors, the filters, the limiting boundaries, the efficiency in those filters, the whole data management system. How sources are detected is actually important, and it's not exactly the same as just taking, sticking aperture, trailed aperture in your object, right? There's actually slight differences in how the data management pipeline will determine what's a 5 sigma source. Vignetting, detection efficiency, linking efficiency, all of these things. And so the idea is that Sorcha takes that plus, right, your input population, so your small body population, your orbits, your cometary activity. If you want cometary activity, you can prescribe it. Rotational light curves, you can prescribe it as well. Phase curves. Your put an absolute magnitude and colors, right, and it will figure out what you should have detected. And so that is what Sorcha is basically nearly there and over the finish line, and it will be ready for people to use very soon. So the idea is that this is a package that really we're building for the community, not just ourselves, and that the idea is that both you can figure out, what will LSST detect or predict, right? What LSST will discover and predict. And Jake Kurlander is going to give a talk all about that next, but also just that you can do your predictions, or you can check your models or tune models based on, learn intrinsic properties. So the idea is it can do, these different tasks. The idea is that you can input a survey pointing database. Right now it's using the Rubin Sim cadence simulation database as input. The camera footprint file, we have a default one for LSST cam, but if you don't like it or you want to do something else, you can. An orbit file. You can provide your own ephemeris. We're using assist and rebound to do things as quickly as possible, but if you don't like what we're doing or you want to modify it and add significant non-gravitational effects because you're really interested in dark cometary objects that have some non-grav effects. You can input that, for example. Again, you prescribe the physical parameters, and things like rotational light curves and cometary activity get input in a separate file that we call the complex physical parameters. So the idea is you basically, as a user, shove all that in, and out, in this black or green box comes the output detection of what LSST would find. And there's an entire, all this is run by a config file or configurable by a config file. So the idea is that if you're doing lots of runs because you're changing one of your model parameters, right, and you want to see how that changes the detections, you can basically keep, you can have all the way you want the simulation to run or how your LSST, right, to behave, that you have already configured it. And so you can just, point Sorcha to a different set of files. And basically every sort of filter and every calculation, you can turn off the things in it. So if you don't want to have randomization, we randomize the magnitudes based on the uncertainty. So it's not just exactly the same value like reality. You can turn that off. So the idea is that we're trying to cover as many use cases as possible. So we might want to predict where an object's located, like in the case of the Rubin Science, Solar System Science Platform, or, if you're running it for predicting where your favorite solar system object is and you want to see where it is really quickly. So the idea is we're trying to think of all the use cases that might be doable and make it as easy as possible for people to do it. So the neat thing, and that's in here, and the really exciting thing is the ephemeris generation. It uses system rebound, it uses a helix grid. So it's going as fast as possible, basically picking 3 points in the night, calculating ephemeris, and then interpolating where things on the sky, but not in our own deck, it's doing it in other coordinates. But the idea is that this quickly and efficiently, better than brute forcing it, can figure out where objects are in the sky. So the only thing I just want to add at this point is we're basically finalizing validation. And so this plot makes me very happy, though Pedro calls it boring, is that this is comparing to, on the Orion deck, our predictions from ephemeris generation to JPL horizons, and they're right on the money. And if we take our output from our ephemeris generation in terms of, heliocentric distance and all those other parameters, and we compare to Pedro doing a complete independent calculation from Sorcha, we're 10 to the minus, 15, 10 to minus 12, we're in the 10 to minus 15 range. So we're at computer precision in terms of what we should be computing for the apparent magnitude. So from all of these checks, it looks like Sorcha's doing exactly what we want it to be doing, which is good for all of you. So basically the idea that we've got this thing running with this link frameworks incubator last year, it really supercharged this thing and made it 150 times basically faster, added lots of different features. And so that, carrying that momentum forward into this current year, we're basically ready to ship this off to all of you in the next couple months. So it's still under development because there's still some bugs we're chasing down in a couple places, and and things that we might want to just improve in usability. Like if pulling Mario away from updating the code, but if he gets his way, he'll keep updating to make it even more user friendly. So the idea is to get as close as possible, and then we'll finish and testing and validation in the next month or so. So we have 6 publications of various stages, including a joint double-A journals and a JAWS software paper that we plan to submit. So stay tuned. We will be very happy to share the code once we are through the rest of the user testing and validation gauntlet.
Great. Questions for Meg? Meg, any questions?
Colin's gonna ask a question. When is it safe for people to start using it and publishing science with it?
When I'm confident it works. So Pedro made that plot last week. So that made me very happy to see it at machine precision. But we don't want to release something that's not 100% right? Because that doesn't make people feel confident using it. And so we're not like, we've now the point where we believe it, we're now using it and we're like, oh yeah, that's not so user friendly, or like that thing's really hard to use. So we're kind of tweaking the UI a bit. And Mario has lots of thoughts. Some of them I let him implement, some of them I don't. He's probably going to wear me down and get them all in August. So we're basically just fit. Yeah, he's probably nodding. So the idea is that we're nearly there. So I would say it's probably sometime in September, October when when we submit the paper. That means we actually have done everything and we're happy with it. So it's close. There's at least a full draft of the paper, or very close to one now. So that means we're filling in stuff. So soon, before the end of the year, I'm pretty confident. But I'm hoping more in the late autumn.
Should we get more questions? We're behind on time as well. We're very full session. Go ahead, Bob.
Thanks, Meg. This is Bob Blum. Last year at the LSST 5, we talked a little bit about the need for compute resources to do some work like this. Is the improvement in speed that you're showing here something that reduces that need, or is it something we should still be talking about?
We still need it, but you helped facilitate, which is that we're currently using Burra, which is the Croatian in-kind IPC. So we have to put into the form to say we would like them to help more formally be able to let people run Sorcha themselves for their own runs, but we've been effectively beta testing, and so it's been quite crucial. So
Super.
The smaller IDACs are really helpful in that case. So yeah, it's on the list to add to our the resource request for the in-kind that we would like to have a IPC. And by the way, we've already got one. Can we have some? Can that be noted that the Croatian HPC is great? So that's coming. And yeah, so we've basically been beta testing it for the science collaboration with Sorcha development. So it's been quite crucial. So thanks for suggesting that at LSST at Europe.
Great. Yep, let's go ahead and thank Meg again. Great. So up next, we have Pedro Bernardinelli, who's going to be speaking on behalf of Jake Kurlander, who couldn't make it. And he's going to be talking about predictions of the LSST solar system object yield.
All right. Hi, everyone. As Sarah said, Jake couldn't make it. This was supposed to be his talk, so bear with me if I do a terrible job. It's not Jake's fault. It's my fault. So as I think everyone here knows, one of the big things we want to do with LSST is have a catalog of our solar system. So then the question becomes, how many objects are we actually going to find? The predictions we've all been quoting for the last 15 years come from the 2009 science book. I think I see Lynn in the room, so you can thank her for 15 years of proposals that you've submitted, but now it's the time for us to try to come up with a better number than that. And as Meg just told you about, we have this thing called Sorcha, which is made to exactly do these kinds of things. So we are running simulations of the solar system at scale. So we basically got the latest and greatest for every single population out there, and we're running them through Sorcha and seeing how many things we're going to find. So we're using the baseline 3.4 cadence. I think this is the latest, so this should be very representative of the current state of the survey. Our linking is meeting the design requirements. This means that there's a 95% discovery chance per 15-day 3-tracklet instance. So what this means in practice is that an object like an MBA or a TNO that gets observed several times over a survey and has a several-year arc will essentially have lots of 95% discovery chances. So essentially get linked in at least one of them. And this also assumes perfect recovery. So if the thing is linked once, this means that we have all the detections of the object. So it is basically the best case scenario, and that's what we're hoping that how we're hoping the survey will work. So our simulated populations here are MBAs and Jupiter Trojans, NEOs and TNOs. So for the main belt asteroids, we're using a scaled down version of the S3M model by Tom Lag. What this does is it has basically 80% of the total S3M population. The reason for this is that some comparisons between data from the Minor Planet Center on the complete regime and S3M show that basically S3M is predicting more objects than there should be out there. We're using CNS colors. These come from spectra that were integrated with the Rubin bands. And you can see here on the bottom, there's this plot of the differential completeness, and this is absolute magnitude. So it's something like 5.1 million MBAs discovered from the simulations. And this is actually very close in line with the predictions from 2009, which kind of makes sense because we use a very similar model. For Trojans, things are slightly interesting. We have 104,000 Trojans, which is a factor of almost 3 less than the predictions from the 2009 science book. We think the reason for this is due to cadence, but don't quote me on this. I am not 100% sure. And here is a cumulative histogram of the number of detections per band for the Trojans, and things look very similar for the MBAs and TNOs. So you can see basically that for the typical object, 50% of them will have 100 or more detections in the RNI bands, a few less in GNR, but still hundreds of detections per object over the 10 years of the survey. For TNLs, we're using the CFAPS orbital model scaled to the Oslo size distributions and the Colossus color fractions. So basically, once again, that's the latest and greatest out there. So these predictions are quite representative of what we expect the TNOs to look like. And we have something like 37,000 objects discovered across these dynamical classes. If you're a TNO person, I know you care about this. If you're not a TNO person, you can just ignore this number. One particular detail is that the scattering population it has this little star here. This number is being dominated by objects at low perihelion and small sizes. This is where we think most of the uncertainty in our predictions is. So this number will probably be different in real life. We don't know in which direction. And it's interesting that in TNOs, you can see these 2 different regimes where you have objects detected by the PhAst deep. They have something like 500 detections at apparent magnitude 23, but things from the mini surveys like North Ecliptic Spur, they have still hundreds of detections, but less than the PhAst deep. For the NEOs, we're using NeoMod 3, which by David Nazorny. I think it's being calibrated on the Catalina Sky survey data. I may be wrong about this. And this has been scaled down to objects greater than 10 meters. Basically, the only reason for this is that we think there are many more objects at smaller size ranges, at the smaller size ranges, so it's much harder to simulate. So Jake's still running the simulations. That's why this number is not there. It's not here yet. And we expect something like 110,000 objects. An interesting detail is that of these objects, about 3% of them have detections faster than the 10 degree per day rates. This is the limit where things get weird and there's confusion with things like satellites. So we have to think a little bit about the risk of linking those objects and reporting them to the minor planet center. And we think this will be higher in the 1 to 10 meter range, basically because these objects are fainter, and so we can get them when they're closer. So that's why you see these sorts of effects. So just a summary of these numbers. We have, except for the case of the Trojans, we actually have a very good agreement with the 2009 predictions to within a 10%. So please, everyone, congratulate Lynn for being pretty much right. And then in 3 years, we can congratulate her again when these numbers are spot on. The only difference is obviously the Trojans. This might be due to the cadence and the position of the Trojan clouds now. And once again, it's also very clear that this is a factor of 10 in a few populations, for example, the TNLs, or a factor of 5 in the case of the main vectors. So just to summarize, we plan to submit this paper by August, maybe September, maybe October. We'll see soon. There's also a paper by Joe Murtaugh coming on predictions on centaurs. Joe is Meg's PhD student, so you can ask Meg about this if you're interested. And with Sorcha, we can also evaluate things like more detailed models, like line curves or some other things like that. And we plan to make this data set publicly available whenever it's out there, whenever it's done. Thank you.
Thanks, Pedro. This is Bob Blum. I'm wondering, can we add the mega constellations of satellites to this simulation to understand their impact under different scenarios?
You can try. I think that what we will see is an is an overall scaling down of the detection efficiency for the exposures. Details someone who understands mega constellations better than me should try to figure out. But in principle, you can try to put this as a module in Sorcha.
I think in practice, this is Mario Urgent. So I think in practice, it should have fairly low impact because one of the things that we see, and I think Pedro had it in one of his slides, most of our objects get re-observed many, many times. So even if you get one observation wiped out by a satellite trail, you're going to have many more chances to see it. So it will have an effect, but it will probably be at a percent level, not as a percent level.
Yeah,
Even
we'll
that
lose a few detections, but the bulk will still be there.
Sorry, I didn't mean to interrupt you, Pedro. I was just going to say, even that explanation and logic is reasonable as something to communicate to folks. That's useful. Thank you.
Yeah.
I just wanted to say once about the thing. Sorry, this is Lynn Jones. So Mario, you're absolutely right. For most of the things, we just see them so many times that losing one detection doesn't matter. Of course, as you get to fainter objects, that is less true. And so for fainter objects, you might see more of an impact, right? Just change the limiting magnitude, the effective limiting magnitude.
Yeah, but then you have the second part of this equation, which is what's the fraction of the surface area on the camera that gets mounted.
Yeah,
onto
it's
the
very
satellite.
small.
And that's an order of a few percent.
Yeah.
So even if you limit yourself just to the faint end, it's still over 2%.
Yeah, it's not.
I know we like to worry about these things, but I'm not. I think we'll be fine.
Yeah. There are some exceptions, of course, right? Like for anyway, yeah. I think we've had this discussion before, right? Like there's some exceptions where it's more important.
We will miss things, but statistically speaking, we've got millions of objects, 2% here and there. Like if we take weather into account, like if we have a really good 10-year stretch, it may be. If we have a really bad 10-year stretch, it may be orders of magnitude worse than what the satellites are going to do.
So there's a reason though that the SUC are starting the near sun twilight survey early, and it's exactly because that is a good place where that might take place. But I wanted to say about the Trojans. First of all, I'm very happy the numbers are very, very close to what we came up with before. One thing about the Trojans, I think you're right, Pedro, when you say like they've just moved. The other thing is the one of the clouds is very close to the galaxy, and we've changed our coverage in the galaxy as well. So that could be another thing that's making an effect there.
Yeah, I should probably write that down because that's a good explanation. It's better than mine.
Well, I mean, and if you look at one of the old simulations, like one of the V1 footprints, I mean, we could even give it to you if you wanted to just run it to just to see out of curiosity. I imagine. The
I definitely want to see that. That's a good idea.
Yeah.
All right, so one more thing from
One other comment. So one thing, like Lynn really has to be congratulated for those numbers. Like there's a prediction 15 years ago, and they've borne out after we knew a lot less about the KBOs at the time, and all these models are updated, and everything seems to be falling around the same numbers. But the other comment to make here is this shows how robust the system is. Right? It means that with all the changes to cadence, to actual details of how we link and detect, but it still remains in the same ballpark because ultimately it's driven by just the aperture and at undo how much we can observe. So this is another proof that when we think about the cadence, we can break things if we do dramatic changes, but generally we seem to be in the right area, and the system seems to be pretty robust to changes. It's good news.
Siegfried has his hand up. All right, Siegfried, one more thing, and then we should probably move on.
Yeah, sorry, just to Bob's question. So we just got an NSF Swift proposal funded to look exactly at, the impact of satellite constellations for solar system objects. So stay tuned. We're going to have some numbers for you soon.
And Meg wanted to remind Bob, we can randomly drop detections out of Sorcha. We do have some mechanisms.
All right, well, let's go ahead and thank Pedro again. All right, so our next speaker is Garrett Levine. He'll be telling us about detecting non-gravitational acceleration in near Earth objects with LSST.
Awesome. Hi, can everybody hear me?
Yes.
Yeah.
Awesome. Great. Well, thanks for joining. I'm Garrett Levine, and I'm entering my final year at Yale in the astronomy PhD program. And today I'm going to talk to you about how LSST can open up a new window into detecting activity on minor planets by detecting non-gravitational acceleration in near-Earth objects. So historically, of course, volatiles have been detected on comets and asteroids pretty much entirely from photometry and spectroscopy. So this is directly detecting photons that have interacted with the outgassing material. A new way in which that has kind of emerged over the last couple of years is to detect volatiles indirectly via astrometry. So if we imagine volatiles outgassing off of a nucleus, conservation of momentum means that it has to deflect that nucleus on the sky. And so if we can see that change in position from a Keplerian orbit astrometrically, that's a way of indirectly inferring the presence of volatiles. So of course, probably the most famous example of this happening was the interstellar interloper Oumuamua, where the non-gravitational acceleration was one of its most confounding attributes. Now, in the years since Oumuamua, a population of near-Earth objects has been discovered that have been called dark comets. Now, this is a nomenclature that I'll adopt for the purposes of this presentation today. And these are photometrically inactive near-Earth objects with non-gravitational accelerations beyond Yarkovsky. So to illustrate what I mean, let's take this scatter plot here of acceleration in AU per day squared versus h magnitude and diameter. So all of these blue dots here are Yarkovsky asteroids, whereas I'm talking about these yellow and purple diamonds up here. These are the dark comets. Now, these dark comets not only have order of magnitude higher acceleration than can be explained by Yarkovsky, but for the most part, they have accelerations in the wrong direction as well. So Yarkovsky predicts accelerations in the A2, the transverse direction, whereas these dark comets are mostly in the out of plane direction. So the fact that the acceleration is too much for Yarkovsky and in the wrong direction warrants a different explanation for these near-Earth objects. So the out-of-plane acceleration suggests that a polar jet might be at play. The outgassing may be happening from the polar regions, and that could indicate some seasonal effects. Of course, this is just a hypothesis. But more recently, a formation mechanism has been proposed where the dark comets would be the rotationally disintegrated sort of end state of these Jupiter family or main belt comets. And so this is a really interesting formation mechanism because it has implications that tells us that dark comets may provide evolutionary context as kind of end members for comets like 67P, the Rosetta target. So this is a really interesting hypothesis, and we would like to test it. Now, all of the predictions of this hypothesis are statistical in nature. So this means that we need a population of near-Earth objects, these dark comets, that we would like to detect and constrain their non-gravitational accelerations to understand the occurrence and what parts of the main belt they may have been sourced from. So thus far, we only know of around a dozen dark comets, but I'm going to propose the hypothesis today with some order of magnitude backing that LSST should enable dark comet discovery at scale. So thus far, all of the dark comets that have been discovered over multiple apparitions. And so LSST compares very favorably to what we would need to do this. If you take a look at this 2005 VL1, for example, this is a typical dark comet, and you see that the on-sky displacement with non-gravs reaches around the arcsecond level if you take multiple apparitions into account. Now, this compares very favorably to LSST, which should have 50 milliarcsecond accurate, 10 milliarcsecond precise astrometry. And so this means that LSST should enable dark comet discovery at scale over multiple apparitions. Now, if we go into DP 0.3.1, we can start to see, or DP 0.3, I'm sorry, we can see that there are, in fact, a number of dark comet candidates that, would they be non-gravitationally accelerating, LSST should have been able to detect it. Now, what's really interesting to me is the fact that LSST may also not only detect multiple apparition dark comets, but it may also have the capability of detecting dark comets on a single apparition. Now, broadly, that's important because that tells us that the outgassing is occurring while LSST is looking. It's not causing some displacement in the years between the apparitions, but it's actually happening in the month or so that LSST gets to see the dark comet. That lets us follow up with Keck or James Webb or name your favorite telescope to possibly directly detect the outgassing with deep photometry or deep spectroscopy. So I can show you at the order of magnitude level why single apparition detections may work. And to do that, let's consider a setup with the sun, the Earth, a near-Earth object, a regular NEO, and a dark comet. Now, these objects look the same. The only difference between them, of course, is that the dark comet accelerates, and that causes some displacement. Now, with an acceleration of about 10 to the minus 10 AU per day squared, this tells us that over about a month, the apparition that we're assuming, this gives us about a 7-kilometer displacement. Now, of course, we know that that's a physical displacement, and we need to convert that to an angular displacement, and that's given to us by LSST's accuracy and precision. So if we want to just detect this at 1 sigma, knowing that we can build up our signal with multiple detections of the same object, the small angle approximation tells us that we can see this from about 0.2 AU away, which means that with LSST's V limit of 24th magnitude, we can detect an H of 27.5 magnitude dark comet at 0.2 AU near opposition. Now that sounds pretty amazing, and that's because LSST is going to be an amazing system. And what's great about this is that H of 27.5 is right in the middle of the dark comet H magnitude range that have been found thus far. These are typically found at between H of 25 and 30, so for H of 25 objects, we should do pretty well. For H of 30 objects, single apparition is probably out of the question. Now we can ask ourselves if our 1 month arc length made a lot of sense. And if we know that typical NEOs are about 6 to 8 kilometers per second, this tells us that they traverse that 0.2 AU in about 50 days. So assuming a 1 month arc for at least this back of the envelope calculation seems okay. Now, of course, I've played things a little bit fast and loose with things like phase angles and things like detection probabilities and trailing losses. And so our next steps here are going to be taking the actual neomod population, running it through Sorcha, and then seeing what the sensitivity of the orbit fit is to non-gravitational acceleration. So this is basically validating this back of the envelope with detailed simulations in Sorcha. So this is going to be a great application of that survey simulator. So to summarize here, LSST should enable dark comet discovery at scale. This would be a novel method of detecting active small bodies by helping us connect 67 P-like comets to NEOs via an evolutionary pathway. And if we can find objects on a single apparition, this would let us directly detect the root cause of activity. And so, of course, as I said, our next steps here are to do more detailed simulations and determine the actual underlying sensitivity of the orbit fit to these non-gravitational accelerations. So hopefully at the next Rubin Community Workshop, we'll have a paper on archive, and I'll be able to tell you all about that. So with that, I'll say thank you so much, and I'm looking forward to hearing any of your questions.
Thanks, Garrett. This is Henry. I was wondering if you could tell us how many objects you expect to pass that close to the Earth, like per year.
Yeah, so I guess I remember when I looked in DP 0.3, we had a few hundred objects throughout the survey that would pass that criteria. I know that the population of objects is going to, in the predictions paper that Pedro was talking about, is going to have smaller objects, and so I would expect that number to go up. But I guess taking the DP 0.3 number, it would be some dozen-ish objects per year. But I would, of course, assume that to go up once you get a lot smaller objects in the full population. I believe that DP 0.3 stopped at H of 25.
Great, thanks.
Bryce.
Yeah, Bryce, go ahead.
Hello, that was a fantastic talk. Well done. So my question for you is, if the sublimation of volatiles is responsible for the non-gravitational accelerations of these objects, what do you think is the most likely volatile responsible for the observed, let's say, implied activity of these objects?
That's a great question. So that I think to really know, you would need to follow it up. I think you would naively assume it would be water, just like based on what is in minor planets. But I think that we need to discover some single apparition objects and follow it up to really know. So I don't want to speculate too much.
All right, well, since we're behind, let's go ahead and thank you.
Thanks.
Great. So our next speaker is Meg Gowanlock, who's going to tell us about the Solar System Notification Alert Processing System, or SNAPS, and specifically asteroid population outlier detection.
Great, thank you. Can you see my screen okay?
Yes.
Yes.
Great, thanks. Okay, yeah, so yes, I'm going to discuss the Solar System Notification Alert Processing System and asteroid population outlier detection. I'd just like to quickly acknowledge the NSF and the state of Arizona. Okay, so before I begin, I'll just give some an overview of the Solar System Notification Alert Processing System, or SNAPS. And so this was discussed earlier today at 10:30 a.m. to 12 in the Alert Broker session by David Trilling. And so SNAPS is a broker that ingests alerts, so observations and metadata from ZTF and soon from the Rubin Observatory. And then we derive a number of properties for each observed asteroid, so light curves and colors and so on. And then we serve a database of measurements and derive properties and broadcast outgoing alerts for objects of interest. And we're only focused on the known asteroids, so we're not doing any asteroid discovery, but I know other groups are doing discovery. So right now we're currently ingesting alerts from ZTF. And like other teams, we're working on, we're using it as a test bed for near future Rubin operations. Recent data release is Snapshot 1, and it has 5 million asteroid observations of over 30,000 asteroids. So you've been using that data set. So one of the main activities of SNAPS is outlier detection. And so we have two types of outliers, and I'll differentiate them here. So the first type is real-time outliers. And so for each object, we determine if its properties its properties deviate from an expected value over time, right? So this is an example. This is a postage stamp of an active asteroid. You see the little tail here. Asteroids are not typically don't have tails, so it'd be an interesting object to to generate an alert on. And so you might look at the time series for this object, and maybe you might see an increase in brightness or elongation or something like that. And that's one type of outlier detection that we're interested in with SNAPS. And Maria is going to discuss this in the next talk. And so what I'm going to discuss is population outlier detection. So for each object, we determine if its properties deviate from the other population of asteroids. So not comparing an asteroid to its prior history, but comparing an asteroid to the other asteroids. And so if we just use as an example the active asteroid that was shown on the previous slide, if we just look at three different properties here, so elongation, the ratio of magnitudes in two apertures, mag 18 over mag 8, and the real bogus score, we can see that here's the data point for that postage stamp that I just showed you on the previous slide. And here are these blue points are a bunch of other observations of other asteroids. And so we would say, well, in terms of these properties, this asteroid is an outlier because it deviates from the rest of the population of observations. So that's kind of the type of outlier detection. One of the types of outlier detection that we're investigating with SNAPS. So in terms of our outlier detection philosophy, there are a few outlying asteroids reported in the literature. There are numerous examples, but there are a few compared to the entire population, and that's to be expected because they're outliers. And so when we're going to be labeling objects as, maybe it's an outlier or not, or when we set an alert that says that this object or this object might be an outlier, we're using an unsupervised approach. And so if you're familiar with machine learning, there's sort of two different types. There's unsupervised machine learning and supervised machine learning. And with supervised machine learning, you typically train a model using class labels. So in this case, you might say, inlier versus outlier. We're not doing that at this point, just because we don't want to create a model that might say that an outline asteroid is an inline asteroid or vice versa. So instead, what we're doing is we're using an unsupervised approach where we simply rank objects in a given feature space from most outline to most inline, or the most typical object in the feature space. And I'll discuss what I mean by feature space in a minute. And then later, after we've detected numerous outliers, so several years into Rubin operations, we're going to investigate supervised approaches for this problem. So I'm not going to go into great detail, but in terms of the methods themselves, we use two GPU accelerated implementations for assigning objects outlier scores. And each method uses two different outlier scoring metrics. So we have k-nearest neighbor searches and range queries as our unsupervised methods. And then each of those has two different outlier scoring metrics themselves. So there's 4 different scores that each object will get in each feature space. And so what that allows you to do is, as a user, to say, well, maybe this set of outlier scores, maybe it's not exactly what I was looking for. Let's try this other one instead. So here's just a sort of mock interface for this. So we have 15 in snapshot 1. We have 15 different properties or features shown on the right for each object in our data set for the snapshot 1 data release of roughly 30,000 asteroids. And so you have these 15 different properties that are probably familiar to most of you. And then what we do is, for each permutation of each of these 15 properties, which span 2 to 15 dimensions, because there's 15 total different properties here, we generate a list of outlier scores. And so it turns out, if you add up all the permutations of these 15 different feature spaces, there's 32,752 total permutations. So we're generating outlier scores for each object for each of those permutation spaces. And the reason why we do that is because you could simply just derive outlier scores using all 15 features, but it's very possible a user might not be interested in some of these properties, right? So you might say, well, I'm not really interested in orbital elements. So you don't want the orbital elements to weigh in on the score for the outlier score itself. So that's why we rederive the outlier scores for each object across each permutation of these 15 feature spaces. So just to make this a little bit less abstract, here's an example of looking at the amplitude from the light curve, amplitude, rotation period of the asteroid, and the average magnitude. And so these are just plotted here. And so what I've done is I've plotted 99% of the points are colored orange. And so these are, we'll call those inliers. And then these black X markers are outliers. And that's, I've selected the 1% most outline objects to be colored black markers. And then, and so you can see that these black markers are these objects are mostly in areas where the inliers are not. And as a sanity check, just to show that, things work correctly, I just looked at objects with an amplitude greater than 1 meg and a rotational period greater than or equal to 500 hours, and just plotted all those with these diamond markers, and it captures them all. So that's just showing that that the method works. Now, of course, this doesn't seem very impressive at all because it's in 3 dimensions, right? So it's like, well, anybody can make a plot and just look at those cutoffs, but this goes up to 15 dimensions. It's just very difficult to visualize 15 dimensions on a plot. So you can get outlier rankings for all 15 dimensions. Okay, so just to conclude this, in terms of Rubin Observatory scales, this was on a 30,000 object data set that was derived using properties from ZTF. We've also parallelized all the computations using up to 4 GPUs to reduce the computational bottlenecks. Because we have these 32,000 permutations, there's a lot of computation to do. And then we created a synthetic data set of 5 million objects, which is roughly the number of objects, number of asteroids will be detected at the end of the 10-year survey. And then we can compute all the outlier rankings across all the permutations of those 15 feature spaces in roughly 12 days. So we're going to regenerate these rankings every few months and make them available to the community. And so we're just making sure that we're able to keep up with that cadence of regenerating all the outlier scores. And so we're mostly capable of operating at Rubin scale. We still have a little bit of optimization to do, but I'm confident that it will work at Rubin scale. Thank you.
This is Henry. Thanks for the talk. Can you do outlier detection on subpopulations? Like, because something like a color might be an outlier in some in the inner belt, but not in the outer belt, or something like that.
That's a great question. So I don't have anything like that developed right now, but of course that would be fairly straightforward to implement. So we could do that. Would that be something that would be useful?
I think so. Yeah.
Okay. Let's chat. Maybe I'll send me an email after.
Yep, we'll do. Thanks.
Mike, this is Wes Fraser. Wondering if you took a look at one hot or YOLO comparison for outlier detection. And
sorry,
I'm curious if you looked at one hot or YOLO outlier detection.
I have not looked at those methods.
Yeah, I will send you an email. I think it's actually a perfect comparison here because you basically compare two source vectors, one that you know the source classification and one that the one hot where you don't know what it is, and it'll tell you if it matches anything in your catalog that is an understood object.
Oh, cool.
It's very used for facial recognition quite well in all airports.
Neat. Yeah, please send me an email.
Okay, well, let's think back again.
Thank you.
All right, so up next we have Maria Chernyavskaya talking about individual outlier detection in LSST using snaps.
All right, give me a second to make it cooperate with me. We all love Zoom. Okay, can everyone hear me okay?
Yep.
Awesome. All right. Hi, everyone. I'm Maria. I'm a third-year PhD student at NAU, and I'm going to talk about outliers, more outliers, with snaps. So as Mike helpfully talked, he kind of introduced snaps. But when I'm talking about outliers, I'm talking about asteroids with unusual properties. And there's two main types, and Mike kind of talked about this, and I'm going to go more in depth. Like we established already, individual outliers are objects who have properties that are changing over time, but it's an individual object here or there. And population outliers are things where you have, groups of objects, and we want to study them in concert because they tell us something interesting about the solar system that way. Currently, we're using data from ZTF. It's an all-sky uniform survey with about 47 square degrees of field of view, and it scans the northern sky every 2 nights and pumps out public alerts that we digest. And we have a data processing pipeline, and we also have a database. So right now, like I said, we're taking things from ZTF, but as LSST data becomes available, we will be processing that. Our first data release, Snapshot 1, has about 30,000 known asteroids and 4.5 million observations, and these are both observed and derived properties. Just to give you a sense of scale of the problem that we're working with, Snapshot 2 coming soon to an internet near you, and that's going to have about 100,000 unique asteroids and 10 million observations. And now I'm going to talk more about the science that we do with this stuff. So let's start with our individual outliers. There's a lot on the slide. Don't worry about it. You have so this is an individual outlier. So we have an object whose properties change over time. That's what the plots at the bottom tell you. They give you the same information just in 2 different ways. So let's start with the plot on the left here. You have absolute magnitude h as a function of time. So if it was just a boring, asteroid, you'd have straight lines across kind of where the dashed line is, but instead we have our red and green filter data points that are clearly something's happening with the magnitude, and we're not sure what. But if you think about it a little bit, maybe it has to do with the perihelion. So maybe it's like, I don't know, active or something. You know, as the object approaches perihelion, it gets brighter and then it dips afterwards. So, you know, we know what's going on with objects like this, and we have a lot of them. And right now, discovery is kind of serendipitous. You know, you give a chunk of data to an undergrad and say, hey, have fun with this, which is lovely. But with LSST, maybe we should be walking away from that and having an algorithmic way to do this. So foreshadowing. And the other type of outlier that we're looking at is population outliers. And this example that I have here, little, you know, participation situation. Where are the outliers? You can't see them. Good. That's kind of the point. Can you see them now? No, you still can't. What if we added another dimension? Oh, there they are. This is a beautiful rotating plot, but it's also a little distracting. So I'm going to go to a two-dimensional, like static version of this. But the point here is when we have more than, you know, two dimensions, we keep adding dimensions and we start seeing these, you know, structures and being able to say, oh, well, there's a population outlier group, and this is how we find out what they are. What we're looking at is a space that has period, the diameter, and the amplitude of these objects. These are all SNAPS objects. And what we did is we calculated the minimum strength required to withstand rotational fission for all of these asteroids. Now, the majority of these points are in black. They don't require anything, any additional strength. They're fine on their own. The colored points are the interesting ones because the minimum strength they require is non-zero, and it's color-coded by the color bar. So the hotter the color, the more strength they require. And we have 456 of these colored points. We're getting somewhere with those points, and we're cross-checking because these objects have periods that are either really close to 2.2 hours or less. And so sometimes period solutions can get a little murky in that area. So we're cross-checking. And about 20% of that 400 and change group turns out to, you know, be values and be something that we believe. So for LSST, that implies that maybe 0.3% of all asteroids need strength. That's fun and exciting. I should note here that the overall period solution fidelity that we have is about 65% or higher. It's just specifically the short period objects are the ones that are a little trickier to work with. And we have two concurrent checking processes to kind of constrain that hit rate a little more that are going on right now. One of them is human vetting. So I'm just looking at these objects by eye. And then we have additional dedicated ground-based observations. And we will have more on that soon. I can definitely tell you when. And, you know, something to keep in mind with as we're transitioning to LSST is that, you know, LSST will be about 10 times the size of ZTF within the first couple of years, and then 50 times as much data at the end. And so all of this checking, you know, it's great and it works now. Kind of, we still want to be mindful of how much, you know, how much we're looking at things by eye and how much we're just doing algorithmically. Again, like I said, currently we're cross-validating by eye. Is that doable with LSST? Maybe. If it's, you know, 0.3 of all the asteroids and we have, you know, 5 million-ish projected asteroids to be discovered, you do the math. I don't know, maybe it would be great if we could, you know, I think what's going to realistically happen is we're going to say, well, here's our first cut. We know that this percent, you know, there's this group of objects that probably have strength, to kind of stay with the example. And then 1/5 of these are actually real. And maybe we don't know exactly which fifth, but maybe that's good enough. Kind of tying into the data size, you know, how do we find these individual things? And especially for the individual outliers where it's, you know, right now we're finding them kind of stochastically. How do we do this in near real time in a way that's algorithmic instead of just, oh, well, you know, let's shell off a piece of data to an undergrad and let them have a fun time with it. And so in conclusion, you know, right now we're doing this stochastic discovery thing for the individual outliers. We're getting good progress on utilizing multidimensional spaces for population outliers, but we do have to keep in mind as we start using LSST how to manage those like low hit rate events in and finding those in high data volumes. Thank you.
Maria, do we have questions for Maria?
I think it's Slack. Oh, here we go. We got one from Meg. Do you want to just unmute?
Can you hear me? I'm not sure my internet connection's strong.
I can hear you.
So you've done a great job explaining how you're going to find all these outliers, and as well as the second talk. How are this going to get communicated to the community? So I hear a lot of talk about a data, like for ZTF, about databases and releases. But we're brokers, so we're a downstream broker. So can you talk a little bit about what's the thinking of when these algorithms identify outliers, what's going to happen? Or so that we can start thinking about how to get prepared as a community, particularly thinking about follow-up?
Yes. Okay. So part of it is going to be, so there's obviously the upstream brokers that take care of all the, oh, hey, we think there's a weird object. Here's an alert, go. And I think we're going to have two processes happening kind of in parallel, where we're going to have, if there's something that's particularly unusual, I don't know, like probably like brightness and things more for the individual outliers, those should be happening in near real time. So whoever, is, I guess, subscribed, however that works, will end up working out exactly. Whoever is listening to the alert stream that we're putting out for the individual stuff, that's probably how people are going to communicate, like get that out. For the like database stuff, this is going to be more like daytime processing. So it's going to be running somewhere in the background on a server. And then when we're ready, we compile it, every, I don't know, we'll figure out a cadence maybe every quarter, something like that. And we're just going to have this like batch that comes out and say, hey, this is a thing now. And, because right now our like the database stuff is basically, we wrote a paper, here's the database with it, come talk to us basically. We might keep doing that. I'm not sure yet. I don't think I make that decision. I don't think I make that decision. So. Did I answer your question?
Sounds like you have a rough idea, but it's TBD in terms of timeline and logistics of how that, like, whether I can decide I don't care about asteroids, I care about centaurs kind of stuff, whether there'll be ability to filter the stream for exactly what I want. For example, like those details are still being worked out, it sounds like. So more, I guess, to come next year?
Yes.
Nothing else from Zoom.
All right, well, let's go ahead and thank Maria again. All right, our next speaker is Bryce Bolin, who's going to tell us about artificial intelligence-powered twilight discovery of Aylos, Atiras, and Comets at Palomar Observatory.
Hello, so I guess I'll go ahead and share my screen. Is that all right?
Yes, please.
All right, I'm going to share my screen right now, and I'm going to hit the play button on this presentation. Here we go. Okay, well, it's great to see you all here. I'm going to talk about a topic that I think is relevant to both current day and near future science with LSST, which is the twilight discovery of asteroids interior to the orbit of the Earth and of comets. So first of all, I'm going to talk about near-Earth objects. Interior Earth asteroids are a subset of near-Earth asteroids. So I'm going to talk about what near-Earth objects are first. So near-Earth objects are, in general, are objects that come within 0.3 AU of the Earth. I'm going to show you a little bit what they look like in our local neighborhood. This is a representation of our solar system as viewed pole on from above the ecliptic plane. This blue circle here is the orbit of Jupiter at 5.2 astronomical units from the sun. And the main belt, this kind of greenish kind of cloud, donut-shaped cloud of objects, is the main belt between 2.0 to 3.5 AU. There's currently about 1 million known main belt asteroids inside this 2 to 3.5 AU zone. But inside of that, we have the orbit of the Earth at 1 AU. So objects which we define as near-Earth objects that come within 0.3 AU of the Earth are inside this dotted orange circle here. There are about 30,000 near-Earth objects which are currently known as of today, about 1,000 of which are 1 kilometers in size. So there are 5 main near-Earth object classes. I'm only going to talk about 2 in detail here, which are the inner Earth objects, the Atiras and the Aylos class of objects. So Atiras are objects that are interior to the orbit of the Earth, but also exterior to the orbit of Venus. So they have an aphelion just inside the orbit of the Earth and a perihelion just outside the orbit of Venus. Presently, there's about 30 of these objects that are known, and it's predicted that 1% of NEOs fall into this category. There's another class of inner Earth objects called Aylos or ALO for short, which have aphelia inside the orbit of Venus, that is within 0.72 AU, and it's thought that less than 1% of the NEO population are ALOs. So how does one go about finding these ALO type objects? Well, for asteroids that are exterior to the orbit of the Earth, they are more or less, they have angles, solar angles, that is the angle defined between that of the object and the Earth, that can range between 0 and 180 degrees. So typically these can found when they're out of solar conjunction more than 100 degrees away from the sun as they pass exterior to the Earth. However, for interior Venus objects, we don't have that luxury. More or less speaking, they have the maximum angular distance between them and the sun is about 47 degrees. So if you plot where in the sky this is, where they're located, the core frequency of where ALOs are thought to be found on the sky plane is within 40 degrees of the sun and around the ecliptic plane. This is a plot showing the ecliptic sky plane distribution of ALOs, where the x-axis is the ecliptic longitude and the y-axis is the ecliptic latitude. As you can see here, where it's this kind of a heat map, the red portion is where the sky plane density of these objects is the highest, and it's within 40 degrees of the sun. So how does one go about looking for these things, practically speaking, from the ground? Well, this is a view looking south of west at the ecliptic from Palomar Observatory on 2020 January 4th at around 7 p.m. Pacific Standard Time. So this is the start of nautical twilight. That is when the sun is 12 degrees below the horizon. So just for practically speaking, I'm going to draw some lines for reference here. The red line is the ecliptic. The orange line is the 20-degree altitude limit of the Palomar Zwicky Transient Facility telescope, which I'll describe in a moment here. But just know for now that it has a 20-degree altitude limit. This yellow box shows the location of Venus, and this green line shows the location of the ground. Now, if I make the ground disappear, we see that the sun inside this purple box here is 12 degrees below the horizon. And so the distance between the area portion of sky that is above that 20-degree altitude limit line is, but yet as close as possible to the sun, gives us this little area here, which I call twilight survey area, which is along the ecliptic shaded in blue. And there's a portion of which would be within that 40-degree kind of sweet spot zone for finding ALOs. So more or less speaking, one has to look when the sun is just recently set below the horizon and as close to the horizon as possible in the direction of the sun along the ecliptic. Just for fun, I'm going to plot where the first ALO asteroid was found, just within this 40-degree kind of sweet spot zone on January 4th, 2020. So we searched for these objects, these inner Earth objects, these ALO objects, using the Zwicky Transit Facility, which is a camera mounted on the 1.2 meter Palomar Schmidt telescope that has a 7x7 degree field of view and a limiting magnitude of 20.5. It can point as low as 20 degrees above the horizon. So this is the survey pointing map on the sky plane, where the x-axis is the sun-centric ecliptic longitude, and the y-axis is sun-centric ecliptic latitude. So Palomar is about 30 degrees latitude, so we most efficiently cover sky that's a bit above the ecliptic, around 20 degrees. And that's why you see in a heat map where yellow is the area of highest frequency of coverage, is around 20 degrees. But we are able to cover sky quite close to the sun, as close as 35 degrees from the sun. So this is a plot showing the performance of the telescope as a function of sun-centric distance. So the x-axis is the sun-centric distance in degrees, and the y-axis is the limiting magnitude. And the heat map in this plot shows the number of visits. And the green is the running average with a 1 sigma standard deviation. So in general, the limiting magnitude of the survey decreases as you get closer and closer to the sun. Starts to be about 20.5 at sun-centric distances more than 50 degrees from the sun, and starts to decrease in sensitivity as you get closer to the sun, falling as around R of 19.5 once you get within around 40 degrees sun-centric distance. So in addition, we also use the global relay of observatories watching transients happen, which is a worldwide network of telescopes in the 1 to 4 meter range, to follow up NEOs that have been observed by Zwicky Transit Facility, including these inner Earth objects. This is done thanks to the help of student volunteers. So I have some here that help me with the search and recovery for these ALO and inner Earth objects. Kunal Deshmukh, Kriti Sharma, Chernyavskaya, and Josiah Purdom were all currently involved in their PhD studies or supporting science. So this right here is a screenshot of the very first known ALO object. The discovery image is the very first ALO object that were taken on January 4th of 2020, which was seen in 4 30-second R-band images and was recovered again later in 2020 and 2021 and 2022. So I mentioned that we also had the capability of finding Atira objects, that is the inner Earth objects. In addition to ALO, we found 4 Atiras, 2020 OV1, 2021 BS1, 2021 PB2, and 2021 VR3. This is a plot showing the orbital configuration of these objects on as if they were plotted on January of 2020. So the bottom panel plot is X and Y view of the solar system, showing the Cartesian location of these objects plotted in 2D space, X versus Y. And the top panel plot is a side view of the solar system, showing where these objects are located in Cartesian X and Z space. In addition to ZTF, Rubin Observatory is planning to do a twilight survey to look for inner Venus objects. This is from a presentation by Lynn Jones, where she shows the survey pointing a solar elongation distribution for the Rubin Observatory baseline survey strategy. And in orange, we have the twilight survey microsurvey. And one thing I want you to notice is that these are highly concentrated towards solar elongations around 40 degrees. So if I plot it compared to the ZTF twilight survey, which is in blue, this is a cumulative density distribution showing for the sun-centric distance distribution of the ZTF twilight survey plotted in blue, where the x-axis is the sun-centric distance and the y-axis is the cumulative fraction. So for ZTF, we have about roughly 50% of all pointings are within 45 degrees of the sun, whereas the Rubin Observatory twilight survey, almost all of them are within 45 degrees of the sun, which is where the maximum angular distance of where ALOs can be found on the sky. So this is a sky coverage map of the Rubin twilight survey. It looks kind of like ZTF's, but pointed upside down. So Rubin Observatory is located about minus 30 degrees latitude. So it's kind of a flip side version of ZTF. So you see this kind of enhancement at around 20 degrees ecliptic latitude. In addition, we trained a neural network model to identify comets in ZTF images. This neural network model, this neural network was used to find a number of long and short period comets. One you might recognize here is called C2022E3, which got, for some weird reason, got a lot of coverage in the media, but it was a pretty looking comet, at least. So all the astrophotographers went crazy for it. And it also inspired the Beaux-Arts. This is a painting of the comet as interpreted by Laura May Abram at Griffith Observatory. So I'm going to leave here a list of publications for work discussed in this presentation, and I'll take questions.
We maybe have time for one really quick question. We're running quick behind schedule. Okay, well, why don't we thank Bryce once more and we'll go on. Great. So our next speaker is Arushi Nath, who will be telling us about accelerated asteroid characterization using PhAst.
Hi, it's great to be here. Hello, everyone. My name's Arushi, and I'm a grade 9 student from Canada. I hope you can see my slides. So today I'll be talking about my algorithm PhAst, which I created to accelerate asteroid characterization, and I'll be talking about why I'm excited about the LSST telescope. So, as you all know, there are over 1.3 million known asteroids, and hundreds more are being discovered every month. And detailed characterization of these asteroids are essential to strengthen planetary defense and further our understanding of the solar system. Yet, more of these asteroids are being discovered than we're able to analyze. So, my project had 3 goals. First, develop PhAst algorithms to accelerate asteroid characterization by combining observations from ground and space-based telescopes. Second, validate these algorithms by measuring the physical properties of the Didymos binary asteroid and measure the success of NASA's DART mission deflection. Finally, apply PhAst to characterize large asteroid populations. So here are 3 main key features of my PhAst algorithm. First, it integrates data from multiple photometry pipelines, including those run by citizen scientists and those from professional observatories. Second, my algorithm creates phase curves, which allows it to generate customized g-values for improved characterization of these asteroids. Finally, it analyzes both dense and sparse photometry data to get phase curves and generate all the physical properties of the asteroid. So here you can see a flowchart of how I'm combining data from space surveys, ground-based telescopes like ZTF, and LSST will definitely be coming in this flowchart once it comes up. So for sparse observations, I use the Gaia Space Telescope, I use the ZTF survey, and in the future, I'll be using the LSST survey as well. For dense observations, I use the mix of the asteroid light curve database by citizen scientists, as well as the asteroid photometric data catalog. And my whole algorithm PhAst is open source, and I used everything from open Python libraries, the open sky catalogs, and open communities while creating the algorithms. So PhAst follows a quick 3-step methodology. First, I removed the effects of changing distance from the sun and observer by applying offsets to benchmark the brightness of the asteroid to 1 AU from the sun and observer, yielding the reduced magnitude. Second, using this reduced magnitude, I was able to plot it with phase angle to create phase curves and find the absolute magnitude and slope parameter of the asteroid. Third, using the absolute magnitude, I was able to combine my dense observations together to find the rotation period of asteroids and, in the case of binary asteroids, the mutual orbital period. Once I created PhAst, I applied it to the Didymos binary asteroid. I was able to create a phase curve by merging dense and sparse photometry. I was able to find all the physical properties like absolute magnitude. I found a geometric albedo to be 0.14, rotation period 2.26 hours, and I measured a 35-minute decrease in the mutual orbital period of Dimorphos around Didymos post-impact. All my results had a strong validation with NASA. After that, I applied PhAst to characterize over 2,100 asteroids, including targets of space missions and binary asteroids and understudied asteroids. I was able to create the phase curves and determine all the physical properties. Here's a short demo of how my PhAst algorithm works. You can see this is a snippet of my code, and I'm able to produce the phase curves. In this case, I'm combining data from the ZTF telescope as well as Gaia. So ZTF is in green and Gaia is in yellow. Since asteroids are not internally differentiated, using the geometric albedo of the asteroid, I could find its composition. Using this, I was able to find the composition of 2,100 asteroids and plotted it with their semi-major axis to understand more about early solar system conditions. I found out that over 58% of asteroids in our solar system were carbonaceous, going up to 75% in the outer main belt, showing that these asteroids were likely formed in the cool, volatile regions of our solar system. So, with the upcoming LSST, this will improve my PhAst algorithm in 3 ways. First, it'll increase the limiting magnitude that's observable, allowing PhAst to characterize much dimmer objects. Second, LSST filters have the LSST survey has many filters in the near infrared zone, and this is very important for being able to differentiate between silicaneous and metallic asteroids, because while these asteroids have similar geometric albedos, in the infrared wavelengths, they differ in their spectral. And finally, using the LSST survey, it'll be able to observe trans-Neptunian objects, so outer solar system asteroids, which will enable me to use my PhAst algorithm to characterize them. So I was able to, with PhAst, make publications in 2 peer-reviewed journals, including a single author in the Acta Astronomica journal, and I was a co-author in a joint paper with our mission in the Planetary Science Journal. And I was very inspired by Vera Rubin's words. No observational problem will not be solved by more data. That inspired me to make my whole code open source on GitHub and provide training modules so that anyone and the next generation can become future citizen scientists and planetary defenders. So in conclusion, my algorithm PhAst was able to accurately determine the physical properties of asteroids using sparse and dense photometry and apply them to characterize large asteroid populations. In the future, I would like to improve PhAst to UR-PhAst using multi-wavelength photometry and expand it to exoplanetary characterization by analyzing transits of exoplanets. In addition, I'm always looking for more observation time on remote telescopes. So if you or your organization has any time available, please let me know. With that, thank you so much. I'd be happy to answer any questions.
All right, thank you, Arushi. Very impressive work. Are there questions?
We have one from Bryce online.
Yes, Bryce.
Hey, hi. I just want to say that was a fantastic presentation. I'm very impressed by what you showed there. Have you thought what might be the most optimal combination of the standard LST filters for determining an asteroid's taxonomic type?
Yeah, that's a great question. And I think by basically plotting all the 3 infrared filters and being able to plot it with the magnitude, I'd be able to differentiate between silicaneous and metallic because those 3 filters are in infrared. And the thing is, silicaneous asteroids and metallic asteroids have different properties there. For example, silicaneous asteroids are more absorptive in those wavelengths, and metallic asteroids are more reflective. So by using the 3 filters I, Z, and Y, I hope to be able to determine those taxonomies.
Very good, thank you.
All right, any other questions for Arushi? All right, let's thank Arushi again. Okay, so that I think concludes our remote speakers. Let me see if I can get this up here. Share this from here.
So you got?
All right, great. So up next, we have Colin and Ryan Chandler talking about scaling citizen science for LSST and the active asteroids program.
All right, hi everybody. This is a little bit of a hard left, but let's do it. Yeah, so I'm Colin Chandler. I'm a product scientist at the LSST Interdisciplinary Network for Collaboration and Computing Link Frameworks at the University of Washington and Drac Institute, where I'm a postdoc. We'll talk today about scaling citizen science. Yeah, for active asteroids program in particular, but your results may vary if you apply this for a different project. We are a NASA partner on the Zooniverse platform. Always you can visit activeasteroids.net to participate, and it is an active ongoing project. We've already heard a lot about active asteroids today, so I'm just going to keep driving home how important they are. Tell us about origins of water on Earth, where volatile are for today and in the past, so solar system evolution, planetary defense implications. This goes on forever. The main thing is we just heard from Arushi, just 1.3 million asteroids, but there's only a few thousand known with tails in a nutshell. So there's some extra special ones with tails, like asteroids that have tails we heard about, and there's not that many of them. So the obvious solution to try to understand these objects better is to find more of them. So we set out to look for more of them in dark energy camera data. This is a public archive for this 4-meter telescope that's in Chile with a giant field of view, and it's got great data quality. This is an image of an active asteroid that actually has a tail going to 7 o'clock. You can see that here. This is our proof of concept that we could actually find things in this data set. And it's great, but the challenge was once I finished extracting all these things, there were like 30 million of them. And even as a grad student, that sounded like a bad idea. So we decided to turn to citizen science. The great thing about citizen science is we're engaging the public in a scientific endeavor, and this is an awesome opportunity. It's also really great for overwhelming tasks. So you hear big data and you hear crowdsourcing. They're perfect for a needle in a haystack problems. There's also less examination bias instead of the features that being derived from just Colin. It's many people examining each object, and it's like 15 nominally. Come back to that. There's potential for AI training as well and involvement, and we'll also circle back to that. So we launched in 2021 with 10,500 volunteers at this point, doing over 9 million classifications. This is what the workflow looks like. It's this simple. We show people a known minor planet at the center of an image and say, do you see a tail or not? That's it. Then these arrows are hiding a lot of underlying steps. So not shown is analyzing the classification data, which result in these candidates, which we vet, and we follow up with telescopes and archival searches to look for more evidence of activity. We do science, which, as last one shows, is in the form of writing code. Yes, we've made a bunch of discoveries already. They're not even all on this screen, not because they don't fit, but because some of them are still in the works. So there's 7 active asteroids and 5 of another flavor, an active centaur out in the orbit between Jupiter and Neptune, and 10 plus Jupiter family comets, with quite a few more on the way. That's awesome. But there's this bigger fire hose coming. I like this picture because a little bit it looks to me like looking down the barrel, but anyway, it's definitely a big fire hose. And just a grand overview of the context for scaling. This is, these are estimates, but 4 million detections per night. That's a little bit daunting. This all depends on cadence and other things which we've heard about today. But we compare this to active asteroids citizen science program. Decam based, we have a total of 35 million. So that means every 10 days, Rubin's going to be generating the same number of detections as we have since Decam's been running since 2012. It's a lot. The rough feasibility at our current classification rates on average, which is awesome, it would still take 150 days of our volunteer effort to classify a single night of LSST data. Not super tractable. So let's talk about citizen science scaling fundamentals. People may not have ever thought about this before. The primary factors are the number of volunteers we have and the amount of participation by those volunteers. I always drop Taylor Swift's name here. If anyone has a direct line, do let me know, because that would change all of these numbers a lot. But besides that, there is another detail you don't hear about a lot, which is how many times each subject is examined. This is true for all kinds of citizen science projects. We can justify reducing this number down to 10 instead of 15 as soon as we have 10 yeses or nos without impacting quality at all. So it's typically a 20% boost in efficiency. So there are these types of gains, but I'm focusing on the number of images to be classified. You could argue that then instead of scaling up, we are scaling LSST down. I do think that's a fair point, but we're going to keep going anyway. All of these assumes you have an optimized citizen science project. And they're pretty much all optimized. They're up there, but That's just a good disclaimer. So we do have betting strategies. So it's obviously 30 million, even going into the project that we have, we wanted to reduce that number. Obvious way would be to reduce the total number through magnitude cuts. So we say not only do we need the object to be detectable in an image, just through estimates of its the depth of the image by exposure, time filter, aperture, all that good stuff, but also is it right enough to actually see a tail evidence of activity, which means a couple magnitudes even deeper. And that is the bulk of that top cut there, 60%. And the bottom we have requiring image data to already be accessed. One of the obvious questions is there a source in the middle of the frame? If there's not, we throw it away. There are a bunch of other ones that aren't even listed here. Those add up to another 10% reduction, which is substantial. We don't need to show junk to folks. So that's 70% reduction, which is great, but we just show those other numbers. It's still not enough. We have deployed this AI assistant called Nath, which is some people consider it a bit embarrassingly simple. It's a prototype. It's trained on our classification data, which is almost all no answers, because this is a very rare phenomenon. All of the volunteers are saying no a lot of the time. So it's supposed to be very good at finding garbage, but we said, what can you really just not tell us is garbage? And it did make 4 discoveries that way. That's great. A couple of active asteroids and a couple other things. Context though, it's 4 out of 35 million thumbnails. It's not like awesome. And so we would like better AI because we know more is in there based on our own experience. What kind of reductions might we get? This is a this is a histogram just showing the number of objects that we can, or cutouts we can choose to ignore based on this score from this AI in 0.1 increments for fractional, 0 to 1. Right now, we're just throwing away stuff that doesn't have a score of a 0.1, which is very low. And we're quite confident, including 2 checks, that it's definitely trash. We would like to work up to a 90% reduction, which if we want to be able to work with Rubin scale data will be a necessity. We do have to keep a fraction easy images. People sometimes forget about this, but if you have like a super difficult citizen science project, nobody wants to participate. I personally have never successfully classified an image with 300 penguins standing on eggs. I've never been able to do it. I don't have the attention. People always ask for resources. We saw from my Gowanlock earlier some resources. I'll just mention here are some stats. Some of them look quite tractable. The main point I would say is just that roughly 100 times as much data from Rubin. With the non-image access vetting, we can get down to 1 million cutouts per night that we would like to look at. That does imply that there's a cutout service that maybe do this for us. And with all of our vetting, we can get this number down about 100,000. So we still need more ways to cut stuff out to look at to keep it realistic. And I do want to emphasize this 25 cutouts a second. That's with everything. This is for assessing everything about these objects. The AI side alone, though, for us, it's been basically requiring GPUs. You could do it with 100 times as many CPUs with a much longer time baseline, but it basically requires GPUs for inference. So yeah, just a quick shot. If you want to just have one takeaway, it's like what could most projects do? You could apply some kind of scientific limits on how much data you want to do. We're going for lowest hanging fruit here, so we know that every one of these is imparting a lot of bias. This is not at all our goal to avoid bias. We want to keep people excited about the project, which means going for this low hanging fruit. We can sort things, get things that are closer to Himalayan distance, so like more likely to be active. We prioritize some populations like centaurs and asteroids so that we get more discoveries at different phases. We prioritize objects that have not yet been examined by anyone. Why look at the same object over and over if you have ones that have never been seen? We can change this AI stuff, and early retirement is, like I mentioned earlier, we do some number of times. Still working on improving AI, setting data quality, like seeing, it's not something that we've had success with, and randomly choosing images. This is the last resort. If we just can't get access to the image data or anything else, we will need to do some kind of broad cut and just take a random selection of the data. I'm going to now go ahead and read the list of participants. I'm kidding. But I do thank all of our volunteers, especially this batch here has been very, very active in our community. With that, here I'll leave the summary set up. Thank you very much.
Yes.
what do you think about having trust scores for very good classifiers and cutting the and weighting those more and cutting the number of required views that way?
That's a great question. There is an expert system built into the universe to do this to some extent. We kind of already do this. We analyze all the volunteers, and you would expect people to get better with time. Some people get worse with time. Some people say yes, they see a tail in all of the images, which is not impossible, and maybe we call this an optimism bias. So we do that already to some extent. Yeah.
You could also talk to someone at CSS with their asteroid detection citizen science project with the universe as well.
Just wondering what the limiting factors of AI making all the humans irrelevant. Like that seems to work for Google. But what's the problem here? Is it just that we're just haven't spent enough time on it yet, or?
That's a great question.
And I'm not trying to belittle the humans. I actually think humans are really important. But,
Yeah.
you know, and I feel like 99% of the work could be done if, you know, the likes of ChatGPT is to be believed.
Yeah, well, my colleague Nima Sedegat has drilled into me that the definition of the problem really drives a lot of these things, and we have defined the problem as finding garbage. That's what we have the most classification data for. So we've trained AI that is great at saying something is definitely garbage. If we want to go the other direction, which we're working on, it just takes a lot more active learning stuff. But I don't expect. I mean, Galaxy Zoo is the launching project for the universe. They are quite in it with AI. They are still running to the science project. Yeah.
Great. Let's go ahead and thank Colin again.
Last speaker.
Yeah. All right. Well, I know that we are already at the end of the session time. We have one more speaker, myself. And so I will try to get through this quickly so that everybody can get to the coffee break. So I will be talking about an introduction to exploring the data preview 0.3 or DP 0.3 simulated catalogs of solar system objects within the Rubin Science Platform. Since this is the Rubin Community Workshop, we wanted to be able to make sure that we covered DP 0.3 in this session. So my name is Sarah Greenstreet. One of my roles is as a member of the Rubin Community Science team. If you aren't familiar with our team, we are responsible for supporting the community in order to maximize scientific productivity and excellence in their or your use of the Rubin data products and services. So we really are here to help the community be able to do their best science with the Rubin data set. So we are here as a resource for you. One of the things we've been putting a lot of focus on recently in order to get us toward operations is focusing on the data previews. In particular, we're focusing on data preview 0, which is happening now, and its focus is really trying to help the community learn about the Rubin data products and the Rubin Science Platform. So one thing that we've been doing a lot of is trying to put together resources for DP0. So you can find all of these resources at dp0.lsst.io. And there's a whole bunch of resources and information here, including documentation on data preview 0, guides to get you started, including how to get an account on the Rubin Science Platform if you haven't done that before. There's also links to a bunch of virtual events that the community science team holds related to data preview 0. One that I think is really useful are our Rubin Science Assemblies, which happen every Thursday at 9 a.m. Pacific. We alternate these between running through examples of exploring DP0 within the Rubin Science Platform and Q&A sessions where you can come in and just ask us any of your questions about the data preview and the RSP, anything you're working on. We can help you troubleshoot or explain things to you. DP0 comes in 2 different pieces. The one that is of most interest for solar system science is DP 0.3, which contains catalogs of simulated solar system objects that include things such as astrometric and photometric measurements, absolute magnitude estimates, and orbits for millions of solar system objects at the level expected for LSST. This DP 0.3 dataset was put together by the Rubin Solar System Pipelines and Commissioning Teams and members of the LSST Solar System Science Collaboration, to whom we are very grateful for this data preview set. So you can find all of the information about DP0.3 at dp0-3.lsst.io. This has a number of resources on this webpage. Some of those resources are to talk about the DP0.3 data products. Here you can find information about the simulated data set and how it was put together. There's also information here about the data products and the definitions, what's in those tables. It includes a description of the tables and what is in those tables. So there's links to the schema browser that includes all of the detailed information about what is in each of these 4 simulated catalogs, which are kind of a scaled down version of what's going to be in the real data set. There's also this new infographic that is on here as well that illustrates the solar system processing pipeline and how the solar system related prompt data products will be getting released on a 24-hour basis. So hopefully this could be another useful resource as well. So in addition to the data products and information about that on the DP0.3 website, there's also a number of DP0.3 tutorials in here that are designed to help the community learn how to use the DP0.3 data products within the Rubin Science Platform. So in my last couple of minutes, I wanted to just run through very quickly a couple of these tutorials, or how the portal and the notebook aspects within the Rubin Science Platform are set up. So to get to the Rubin Science Platform, you can go to data.lsst.cloud. If you have never gone there before and don't have an account, you can click on the documentation tab, which gives you all of that information, including getting started guides, like how to get an account on the Rubin Science Platform. So once you sign up for an account and you can log in, the best place to start looking is to go to the portal, which is a good place for getting an initial exploration of what the data sets are like. So this is the landing page for the portal aspect of the RSP. And you can see at the top here are the different DP0 data sets that you can click on. DP0.3 only has simulated catalogs. There are no simulated images for the solar system simulated data set. So if we click on DP0.3 catalogs here, you can see at the top, you can choose which of the 4 tables you would like to look at. Once you've selected one, this is the MPC orb table. It will show you what is in that table, all of the columns that are listed there. You can then choose any of those parameters you'd like to look at or explore. You can also add additional constraints to the values from those parameters that would be returned to you. And then you can choose how many rows you want back. By default, there's 50,000 that will get returned to you. You click the search button and it will return to you your set of, in this case, 50,000 objects with all of the parameters that you chose. And then you can start exploring the data. You can make plots of those parameters. So you can do scatter plots or histograms or heat map plots. And so it really just gives you an interactive way in the browser to be able to start exploring what the DP0.3 data set looks like. So it's a good place to get started if you're new to DP0.3. And we also have a number of tutorials that can walk you through how to be able to explore the portal, what all of the different buttons do, and how you can make plots like the ones I just showed within the portal. If you want to do more in-depth exploration of DP0.3, you can use the notebook aspect. This is the landing page for the notebook aspect. It's essentially Jupyter notebooks within the cloud. And so you can click it on a terminal here, and you can be able to access your own space that you're allocated within the RSP. If you want to, we have a number of tutorials in here as well for how to explore DP0.3 within the notebook aspect. These go through a few of the different small body populations, such as near-Earth objects, main-belt asteroids, transit-2D objects. There's a tutorial in here on constructing phase curves of solar system objects, including more advanced modeling. And there's also a tutorial in here on uploading your own tables if you want to be able to compare the simulated LSST data set with other data sets as well. Gaia is the one used in this example. And you can also create your own Jupyter notebooks. So you can look at the tutorials, or you can start building your own tools and notebooks that will allow you to start exploring DP0.3 and get ready for the data set once it is here. So the notebook aspect gives you a little bit more in-depth analysis opportunities. It comes with some pre-installed libraries that include things like SVPy, and you can also install your own tools, and you've got compute resources allocated as well. And again, there's a number of these notebook tutorials. So quickly, if you want to get started with DP0.3, you can get an account at data.lsst.cloud. There's documentation to help you get started. You can always ask for support on the Rubin Community Forum as well. The community science team monitors this every day, trying to get people answers to questions as quickly as we can. And you can also attend the weekly Rubin Science assemblies to ask us questions as well. And of course, you can always ask a community science team member as well. Again, we're here to help you be able to do your best LSST science. And so please use us as that resource. Thank you.
Any questions for Meg? Sorry, Sarah. From Meg. Just a thing.
Do you have a sense for how much usage do we see on this data set, and what kinds of queries do people write? Are there any things that we can learn inside the project based on what we're seeing right now with the tests?
Yeah, I've seen that question come up in a couple sessions so far, mostly asking about the overall number of RSP users that there are. I don't think we have a lot of the details about whether people are specifically using DP0.2 or DP0.3. I think so far there's roughly 1,000 active accounts on the RSP, or people who have at least started the process of signing up for an RSP account. But as far as whether they're using DP0.3 or not, and what types of queries they're doing, that information is probably available by the RSP team. But I don't know the answer to that.
Do you maybe know if the queries are recorded so that they can be analyzed later?
I don't know the answer to that. I don't know if they are actually recorded or not. An interesting question, though. All right. Well, thank you everyone for staying so late to the session. I'll thank all the speakers again.
The online presenters haven't uploaded their talks yet, please do so. Thank you.
There was no guest sightings in this